Good morning, good afternoon, good evening, good night. No matter what the time, you're always welcome to my presentation on hydrogen fuel cells, presented by yours truly, Tirth Nagar. Welcome to a section I like to call Fuel Cells for Dummies. Let's start with some basic information. Fuel cell basics. Fuel cells function similarly to batteries except they do not deplete or require recharging. They continuously generate power and heat if fuel is made available to them. A fuel cell is a device that produces energy through an electrochemical process rather than combustion. Hydrogen and oxygen are combined in a fuel cell to generate electricity, heat, and water. Parts of a fuel cell. A fuel cell consists of two electrodes, an anode and a cathode, sandwiched around an electrolyte. A fuel such as hydrogen is fed to the anode and oxygen is fed to the cathode. In a hydrogen fuel cell, a catalyst at the anode separates hydrogen molecules into protons and electrons. The electrons travel through an external circuit, creating a flow of electricity. The protons migrate through the electrolyte to the cathode where they unite with oxygen and the electrons to produce water and heat. Now let's dive into the properties of elements and compounds that are involved in this oxidation reduction reaction. Starting with hydrogen. Hydrogen is the smallest chemical element since its nucleus only contains one proton. Its symbol being H and an atomic number of 1, hydrogen is the lightest element with an atomic weight of 1.0079 atomic mass units. Hydrogen is a non-toxic, non-metallic, odorless, tasteless, colorless, and highly flammable diatomic gas at standard temperature and pressure. Hydrogen contains just one proton and electron. Protium, the most abundant isotope of hydrogen, has no neutrons. Hydrogen has a melting point of negative 259.14 degrees Celsius and a boiling point of negative 252.87 degrees Celsius. Hydrogen has a density of 0.08998 grams per liter, which is less than that of air. It also has two unique oxidation states, being positive one and negative one, allowing it to function as both an oxidizing and reducing agent. Next up, we have the properties of oxygen. Two atoms of oxygen join at standard temperature and pressure to generate dioxygen, which is a colorless, odorless, and tasteless diatomic gas with the formula O2. Oxygen has a symbol O and an atomic number of 8, with the average atomic weight of 15.999 atomic mass units. Oxygen has a density of 1.429 grams per liter. Oxygen is a powerful oxidizing agent with the second highest electronegativity of any reactive element. Oxygen is also found in major types of structural components in living creatures such as proteins, carbohydrates, and lipids. The melting point of oxygen is 218.4 degrees Celsius, while the boiling point of oxygen is 183.0 degrees Celsius. Lastly, we have the properties of water. At standard temperature and pressure, water is a liquid. It has no taste or odor. In the visible region of the electromagnetic spectrum, water is transparent. Water can act as both an acid and a base. Water is a polar covalent molecule. Water has a great capacity for heat, meaning it takes a lot of energy to raise the temperature of a specific volume of water by a degree. Water aids with temperature regulation in the environment. Because of their capacity to hydrogen bond, water molecules exhibit high cohesive forces. Water also possesses adhesive characteristics which allow it to adhere to things other than itself. Next up, I'll be talking about the chemical reaction taking place in a hydrogen fuel cell. At the anode takes place an oxidation reaction, while at the cathode, a reduction reaction takes place. As a side note, just so you know, both these reactions are complete opposites. An oxidation reaction is one where there's a loss of electrons, or the oxidation state of a molecule, atom, or ion is increased. A reduction reaction, the opposite of oxidation, is a process where there's a gain of electrons, or the oxidation state of an atom, molecule, or ion decreases. The simultaneous occurrence of both these reactions is known as a redox reaction. You can see at the top, illustrated by the chemical equation, that when 2 moles of hydrogen gas are introduced to the system at the anode, 4 moles of hydrogen are separated from their respective electrons. And at the cathode, we have 1 mole of oxygen in combination with 4 hydrogen atoms, plus the 4 electrons which were previously separated, are combined to make 2 moles of water. Over here we have a simple demonstration on how a hydrogen fuel cell functions. On the left we have hydrogen gas being supplied to the anode, where a catalyst is present splitting the hydrogen atoms up into protons and electrons. The electrons travel through an external circuit providing a flow of electricity, while the protons travel through the proton exchange membrane, both of which meet up on the right side together, combining with the oxygen being supplied to the cathode to produce water and heat. Now let's talk about the environmental implications of hydrogen fuel cells. Producing hydrogen fuel cells does not damage the environment if renewable resources are used in the manufacturing process. However, the production of hydrogen is not necessarily environmentally friendly. The extraction of hydrogen from water is a costly process. Therefore, it's cheaper to produce hydrogen from non-renewable sources such as oil and natural gases. Ironically, the carbon dioxide emitted during these processes of creating hydrogen from fossil fuels cancels out any environmental advantages. Hydrogen emissions can also raise methane loads, degrading the ozone layer and adding to global warming. Now let's talk about the effects of fuel cell technology on humans. The primary risks of fuel cells and hydrogen-powered cars are electrical shock and fuel flammability. Many fuel cell car motors operate at voltages which are greater than 350 volts, which is more than enough to kill a human heart. The second source of worry is that fuels utilized to power the future generation of automobiles. The hydrogen used to power a vehicle does not necessarily have to be kept aboard the vehicle as hydrogen. Hydrogen can be reformed in the vehicle, which can also be utilized to power a traditional internal combustion engine. There are numerous methods of storing hydrogen in a vehicle, including reforming hydrogen in the vehicle itself. Each of them has its own set of flammability hazards. Now that we've talked about the pros and cons of hydrogen fuel cells, let's look at some alternatives. Fuel cells are typically powered by compressed hydrogen. However, a variety of liquid fuels can be employed within the fuel cells. Because hydrogen must be stripped off the fuel molecule and then utilized in the fuel cell, liquid fuel types may not be as efficient as pure hydrogen, depending on the system's design. Hydrogen can be stripped from the fuel molecule outside or inside the fuel cell. Methanol, ethanol, and ammonia are among the many fuels processed inside the fuel cell. Methanol is an alcohol-based fuel with a significantly higher energy density than compressed hydrogen. Methanol is an appealing fuel for fuel cells since it's readily available in the supply chain. Approximately 90% of the world's methanol is manufactured from synthesis gas from natural gas. Methanol can also be produced from non-petroleum feedstocks such as coal and biomass. Approximately 75% of methanol is used for chemicals, and the remaining 25% is used for fuels. Thank you for coming to my presentation on hydrogen fuel cells. If you have any questions, please let me know. Have a great rest of the day.